So hello, welcome back guys. This is my second video on our Devlog channel, and today we're gonna talk about how you can create your own file format. First of all, you might want to say, why even create your own file format? It's just simple. Put a database in front of it and finished. Yeah, sure, that would be the easy way, but where's the suffering and all the fun? So today in this video we're gonna talk about how you can create your own file format and how we've done it for Observe. This video is gonna be split into two parts. The first little part is about what we've done with Watchtower and the storage solution there. It's not going to be a long part, it's just for documentation wise. The second part is way more interesting, and it's about the custom file format and the storage solution at Observer. If you're just here for the custom file format, feel free to just skip ahead. So, okay, why go through the trouble of creating your own file format? It's just easy. Put a MySQLite database in front of it, or a DuckDB, even better suited for our metrics, and yeah, you're done. Sure, that would have solved it and would be an easy solution for our problem. But one part about Observe we haven't talked about yet. It's that we may in the future want to be compatible with embedded devices. And there, a database like MySQLite or DuckDB is not suited well, because when we start a connection pool there, we don't have power over the resource usage. And what I mean by resource usage exactly, we can open the connection, sure, but when we use a library for this, we don't have full control on when stuff is written, how it is written, or even in which data blocks. And therefore on devices with very little compute power, we can't risk it to kind of block other services from running. And even a whole database is totally overkill for this usage, and therefore it made much more sense to kind of build our own storage solution. A little bit of context about Watchtower before refactoring. Watchtower, as to this date, has a timescale DB with hypertables for the metrics. To be honest, this wasn't my idea. A colleague from university told me about timescale DB, and it fit our use case really well. Since we were using Postgres in the first place, it was just a drop-in replacement and some logic on startup to convert our tables to hypertables. So yeah, and it had I think a performance gain about 15 to 20 times, not percent, so it was really insane, and therefore we kept it this way. Okay, now to our file format. The choices we made are really tied to our specific limitations and what we wanted to achieve. And to know a bit more about how we build it or why we build it this way, let's first look at our requirements. The first one is that it needs to be quite versatile. We are changing the layout of the collectors quite often, and also planning in the future to adding new metrics, so it would be bad if all is fixed for now. So, first requirement. The second one is that it needs to be quite tiny. It should take up very little space. But this isn't about the format at all, to be honest. It's more about our serialization and our compression in the first place. But this is also a requirement, so it needs to be tiny. The third one is that we can split it up into multiple files and therefore have kind of a timestamp from the first metric which is in the file and the last metric which is in the file, to be able to skip around multiple files in the directory. Another one is data integrity. I think everybody agrees on that we don't want to have errors in our metrics, and also being able to kind of validate if the whole file is gone bad or just one storage block is bad. Therefore, multiple checksums. Another part to our project is that we want to store metrics for a few hours or even weeks in quite good detail. But after that, we can delete many records. We don't need the resolution of half a minute for metrics which are kind of 2 months away. So it should be able to delete metrics on the fly with a background runner, which go through, deletes whole files or just simple parts out of it. So we kind of need the logic to not place whole chunks of data in this file and not being able to delete single entries. Therefore, we can serialize a whole lot of data, store it into one file, and then later deserialize it and store it right back in after we deleted our entries, because that would be much more computational power than we can afford on our embedded devices. So our solution there, split data into multiple blocks and make them extensible with kind of a unique data type, so we know what's stored in upfront without deserialization of the whole data block. Also have a field for when the data was created and when the block was created. We need that later on for time-based deletion. So that's another requirement. There are also lots of good papers I read for custom data design, and I can put them into the video description down below. So let's look into our custom format. In the header, the first few bytes are our magic bytes. I copied this, to be honest, from the articles I read, and it's from my understanding that each service or each format has its own few bytes in upfront to like kind of organize and know that this file type is really suited for the application. On our part, it's obvious we put observer there in binary. And then the next byte is for the version. Let's hope that there are not 256 versions out there and we need to make another one. But let's be honest, if we don't get it right in the first 256, maybe there shouldn't be a 257th. Okay, now the first data bytes. The block count counts how many data entries are there in our single metrics file. And U32 is quite a lot, but when you compare it to U16, a U16 with our compressed metrics format is about like 3 megabytes to 6 megabytes, depends, but that's quite low, I believe, for normal usage, and therefore a U32 is much more suited. I don't believe we're gonna do 100 gigabytes of metrics format, but yeah, those 2 extra bytes, I don't think they're gonna hurt. Then we have 2 really useful fields. One is for the first metrics timestamp and another one is for the last metrics timestamp. Those 2 mark the first and the last metrics entry which are stored in this file. We plan on just storing one type per file, and therefore it's obvious when we have, let's say, CPU metrics in this file that we can delete from a specific time range and not disrupt any other data fields because it's just one type in one file for now. And the last field in our header is a CR32 checksum. So it's just a hash on our fields in the header to be safe that it is stored correctly. Then let's skip to the more interesting part. We have our block. To being able to skip over the data really fast, we need to be able to get a size of a block really fast in the first few bytes, because otherwise we won't be able to know how long a block entry is without reading through all the bytes. Therefore, the first field is our serialized data size. It's a U32 and gives the size of our data in bytes. Then we have our data type. It's a U64. I know this is quite big, but Rust provides an option where you can give a data type, a struct, and then you get a U64 hash back, and we are just going to use this for identification later on when deserializing the data back. Then as the next field we have our serialized data. This is a vector of U8 values and yeah, just a serialized bytes, nothing more there. The next value is gonna be the data creation time. We talked about it before, and it's the value where we can determine when the data was collected. After that, not to be confused with the value before, is the created at timestamp. This is gonna be the timestamp when the block actually was created. This comes in handy later because we want to know when the block was actually created. The block is not gonna be created when the data is gathered or even when the file is saved to disk. This is because first the data gets stored into a cache in memory in our application and later gets transferred to a block, and if all blocks were created, then it's going to be saved to a file. Last but not least, we have another checksum. This is also a CR32 checksum, there for the integrity of one block. Yeah, and that's basically it for the theoretical part. To be honest, I thought it would be way more complicated to create your own file format, but in the end it makes sense. You lay out the data how you want to do it, and then you're just saving it to disk and later can load it back in. During testing for the resource usage, it was quite nice, because we first save it to our in-memory cache. We don't have a lot of disk writes, which is fast. It also protects embedded storage on tiny devices, because many reads and writes can damage the storage on board over time. And the other cool parts about our custom data format are, first, I've learned quite a lot how to layout data and how to even save it to disk. I first also thought that I can write my own serializer, but after looking into Serde, the main serialization library for Rust, I quite fast saw that this is a whole nother topic which I'm currently not ready for. Who knows, maybe in the future. But for the technical advantages, we don't rely on any database system, on any library for our data to be stored to the file system. We now have a way to run it on every machine, everywhere, on routers, embedded systems or whatever, and I think that's pretty cool. We solved all our requirements with being as minimal as possible, having a way to skim over the data, sort it, or even delete it out afterwards. We can run on pretty much any machine. We can turn up the caching and make it more aggressive, so even less is saved to disk for devices where we don't even have that much space on disk. Therefore, as said, I think that's a pretty cool solution, and hopefully we're gonna see us in the next video. This is gonna be the first time that we are actually going through code from Observer. So hopefully see us there, and to our fellow 3 watchers which are now at the end of this video, thank you for watching, and yeah, hopefully you had fun.